Okay, Le Chatelier's principle. Le Chatelier, named after a French gentleman. It's the idea that when an equilibrium is disturbed, the system will shift to make up for the disturbance. And the cute little cartoon, which no scholar state would ever do. Too much homework? Throw it in the fire. Okay, but it actually does kind of get at the idea. A system in equilibrium will fix itself. Or I should say, a system whose equilibrium is disturbed will fix itself. So in chemistry, what that adds up to is that if you add or subtract something from an equilibrium, you're going to shift it toward one direction or another. Here's what I mean. And we can use this as an idea, or this is an example, a non-chemical example, because this is a physical change where H2O is becoming H2O. So ice plus energy, we all understand energy is heat. So ice, add heat, it becomes water. Water can become ice as long as the heat becomes separate from it. If you separate heat out, that means, of course, cooling it down. So separate the heat out, it gets colder, it becomes ice. Add the heat in, it becomes warm, it becomes water. So here's the thing. In general, if you add something, it shifts away from what you add. If you remove something, it shifts toward what you remove. So if you add energy to the system, this is how we're going to look at it from equilibrium, Le Chatelier's point of view. If you add energy, it's going to drive the reaction away from what you added, this way. If you add something on the left, it drives it away from the left toward the right. So we say the reaction shifted toward the right, and because of that, you're going to get less of whatever's on the side you added to, and more of whatever's on the other side. Had I added, so theoretically, had I added water, I would get more energy and more ice. Had I added ice, I would have got more water. Theoretically, okay? Now, the analogy breaks down at a certain point because this is a physical process, not a chemical change. But with chemical equations, it really does work. And this is the same process you would use. So whatever you add, it shifts away from what you added toward the other side. So if you add something on the left side of the arrow, it shifts toward the right. If I were to add something on the right side, it would shift toward the left, which means more of whatever it shifts toward and less of whatever it shifts away from. So that's what this is all about right here. So more water, less ice, because it's shifting toward the water side of the equation and away from the ice side. All right, next. What if you remove something? If you remove energy, you're getting it colder. So whatever you remove, it's kind of like at the beach. If you dig a hole in the sand, water comes in, and the more you remove, the more water comes into your hole at the sand, and more sand, whatever. Same idea here. If you remove energy, it's going to make it shift toward whatever you removed, which means you'll get even more energy as water turns into ice and releases its energy in the process. So whatever you remove, it shifts toward the side of the equation, or rather the side of the arrow on which you removed something. So you remove something on the left, the equation shifts toward the left. If I were to remove water, the equation would shift toward the right, and I would get more of this formed and less of this. So because I remove what's on the left of the arrow, it shifts this way, which means more of whatever's on this side and less of whatever's on this side. All right, so this is what that all comes out to, okay? This is the important take-home message. Add something, it shifts away from it. Remove something, and it shifts toward it. So an actual chemical system, here's the simplest possible one. It gets the idea across. So the way it works, okay, so we look at this one right here. Oops, I see that the numbering is not correct, but it works. Okay, so the Chatelier's principle. Consider a closed container with these two chemicals. If you add this one, what will happen? So if whatever I add, and you need to repeat this to yourself, whatever is added, the reaction shifts away from it. That means if you add what's on the right, it shifts away from the right toward the left. What shifting toward the left means is you're going to produce more of whatever's on the left side of the equation. So that means more of this produced. Okay, that's going to be the effect of adding more of this, is you get more of this made. Okay, what about here? Okay, consider a closed container with the below reaction at equilibrium. If it's removed from the container, then what will happen? Okay, remember, what you add, it shifts away from. What you remove, it shifts toward. If you remove something here on the right side, it's going to shift toward the right. So if you remove something on the left, it's going to shift toward the left. So it says you're removing nitrogen. That means you're removing this. It's on the left side. It'll shift toward what you removed. There you go. It's on, so it shifts to the left, which means when shifting toward the left means you're getting less of whatever's on the side it shifts away from and more of whatever's on this side. So that's why we're going to say produces less of this and more of these. Okay, so it's basically, it's all flowing this way. Now, with these right here, okay, so what if you remove from a container, what will happen? Okay, think about that for a moment. Do you remember what happens if you remove something? Hopefully you said it shifts toward it. And so it says you're removing this. Which way would you say it would go? Hopefully you say toward it. So that means if it's on the right side, reaction shifts toward the right, which means more of whatever's on the right and less of whatever's on the other side, the left. So this means more of these and less of these, as you can see. Let's see, yeah. All right, now, one of the things to consider, okay, what if you heat it up? We can do other things, right? Instead of just adding subtracting chemicals, we can change heat. Well, wait, where's energy in here? Because heat is energy. And the answer is, this is energy. This stands for kilojoule, and that's energy. Okay, a kilojoule is a measure of energy. So in other words, we have energy on that side. So it says you heat a system up. That means you're adding energy. So if you add, then you're going to see the system shift. Well, actually, take a moment, pause this video if you're watching, predict which way it's going to go, and then I'll continue in a sec. Okay, hopefully what you said was, if you add this, it shifts it away from what you added, which means you're going to get less of this and more of this. So that's why I say shifts to the left, less ammonia, more hydrogen and nitrogen gas. Now I might put kilojoules or I might spell out the word energy. Same thing, it doesn't matter. I could also put J for joules. Same thing, it doesn't matter. It's all energy. It's cooled. That means remove energy. So cooling down means removing energy. That means removing this. Take a moment to predict how it's going to shift, what you can get more or less of. Pause, and then I'll explain in a sec. Okay, so what you should get is removing this. You're going to shift toward it. So that's a leftward shift, which means more nitrogen and more oxygen, less nitrogen monoxide. Okay, next. Aside from temperature or adding or subtracting a chemical, you can change other things about these items. So, okay, what about changing a volume? So suppose it's the equilibrium where the gases component is compressed by decreasing the volume. How does the Chatelier's principle predict that it will respond? Okay, first of all, pressure only affects gases. So we ignore this, not a gas, ignore this, not a gas, so just look here. We notice gas is only on the right side of the equation. Well, gas needs space. Gas likes space. So here's the thing. If you increase the volume or the pressure, if you increase the pressure or decrease the volume, decreasing the volume means shrinking it. That means pushing it away from things that like space. Things that like space don't like it when it shrinks. So that means it's going to shift away from the gas if you decrease the volume, because when you decrease the volume, stuff that needs space becomes uncomfortable, so you're going to shift it away from stuff that needs space. Which is why you're going to get a leftward shift away from the thing that needs space, toward this side of the equation where there is no gas. And because of that, if you're going to shift toward the left, that means more of this is made and less of these things will be made. On the contrary, if you expand the volume, that's going to favor things that like more space. Now wait, these are all gases. So which one do you choose? You have to remember what a balanced equation tells us. Is this balanced? 1 phosphorus, 5 chlorine, 5 chlorine. Okay, balanced, that's good. But notice a balanced equation tells us a ratio of moles. So there's 1 mole of gas on this side. This is 2 moles of gas. 1 mole of this plus 1 mole of this. So 1 mole of gas, 2 moles of gas. It doesn't matter what kind of gas, we don't care. We're treating all gases as the same. So because of that, we can say that there's 2 moles of gas here, 1 mole of gas here, 2 moles of gas. That stuff likes having more space. More gas needs more space, less gas needs less space. So if we were to shrink it, that would favor the part that takes up less space, that would favor this. If we expand it, that favors the part that needs more space. That's this. So that we do. Increase the volume. That means you're favoring the part that needs more space. You're favoring this one. And what that means is a shift toward the left. The part where there's more moles of gas is favored when there is an increased volume. So because of that, you're going to wind up with more of these and less of these. Okay, so what about this one? Let's see. We compress it by decreasing the volume. Let's see. Decreasing the volume. Less volume means less space, which favors the side that has fewer moles of gas. We need to figure out which one has fewer moles of gas. Let's see. 1 mole plus 3 is 4 moles of gas. 1 plus 3 is 4 moles of gas. Okay. What we see here, therefore, is a situation where we have equal numbers of moles. Which means if you have a situation where we favor the one that's less moles of gas, but they're the same moles of gas, neither one is favored. Because of that, neither one being favored, we say the reaction shifts in neither direction, which means the amount you have doesn't change, just stays the same. Look at this one. The system is compressed. That only affects gases. If you compress or expand or increase the pressure, decrease the pressure, whatever, it doesn't only affect gases. Look, there's no gases. If there's no gases, then there's no effect. No shift either direction, which means no change in the amount that exists. The equilibrium is unperturbed. It is not affected. Okay, so that is essentially a look at all the different types of ways we can look at a Chatelier shift. So there we have it.